let us start. So just a minute. Let me ask you some questions. So, I think you have submitted the assignment. So, may I ask you that? I mean, any one of you have understood the paper that this fat one clearly? If someone of you has understood, then I shall request him or her to explain it a little bit, and then I shall explain. So once I finish this, a little bit of bonding part is left, and that I shall finish first, and then I shall go to the discussion of this fat, and then we'll go to the new topic. So maybe we can take it a little 5 to 10 minutes break in between. So, is there anyone who have understood the this paper, this fat? So, or anyone is interested to discuss it in the class? You can write in chat because I now I'm here. Okay, I shall. You can keep. Write it, and I shall come back. Okay, so till now, the type of interactions that we have encountered is the sigma and pi interaction, right? So this part is uh, mainly from organometallic sides, and you will learn it very well during this, of course, this when you in the fourth year transition metal 2, you will learn it very well. But for now, at least when you are learning the bonding aspects of the this transition metals, then you must uh, have some idea that how does it happen, and it is not that difficult to understand because you have already understood the same. I mean, how these bonds are interacting. So here it is a pictorial depiction of the bond. So let us take a very simple example, right? So if you have, so let us build it. Okay, so if you have M, so you have this one as a six orbital, six ligands approaching from the say this octahedral symmetrical way, and this is octahedral symmetry. Now, if you remember that if we remove one of them, so let me take a new page so that I can make it clear, and then I shall come back. Someone wanted to join, I think. Not visible. Okay, so what we are planning that Cl. I am not. I shall not write Cl right now. Okay. L. Now, if we, for instance, if we just want to do this, then what is the geometry? This is the geometry, right? Now, if you bring another these unit, then these there will be a metal bond. Now this bond, what will be the nature of bond, how many bonds will be there, and what is the orbital overlap picture, that will be determined by the nature of metal, the electrons, and available things. Now, what are the simple things? So, if you just do it, and if you remember that it was an EG orbital for octahedral, and then it was dx2y2, dz2, and dxy, dyz, and dxz, right? And when we go to square bipyramidal, then dx2y2 remain as its place, and then dz2 lowers because one of the ligand from z axis is this goes, and a little bit of lowering of this yz and dxz and dxy. So all of you I think remember, but still I do it. Now let us go to understand the what are the interactions. So these are this portion is free. Now what are the metal orbitals? For a little bit of time, let us forget about the presence of the ligand, and let us see that what are the orbitals that are available. Now, first instance, if you just look at this was the this orbital was the z orbital, dz2 orbital, right? I cannot do it. So if it is like this, then if you remember, I mean, again, I am bringing a little bit hybridization concept of this, that when these orbitals is removed, this L is removed from one of the Z axis. Please try to understand, and if you do not understand, I mean, tell me, I shall explain it once again. So when you are removing one of the orbit ligands from the Z axis, then what happens? If you remember that there is a pz orbital of metal also. So pz orbital of metal, and there was dz2 orbital, and the point is that as this part is anti-bonding, as you know, for dz2 this electron, this is an anti-bonding interaction, if you remember, for ml6 octahedral. So there is a if there is a space, it will try to distract from this side, and what is this now? It is a little bit of like this. So this is actually pz of metal and dz2 of metal. So they become, so it is either you try to understand, and even if you do not understand, you just think of that the one lobe of the dz2 orbital is available towards this side. Now if these two comes, now if we, I mean, now they have, what they have done, they have just rotated the molecule so that we can write this is the z axis. Now you can see this is the z axis. So there will be a head-on overlap for dz2, either or we can write dz2 or hybridized dz2. And what will happen? This will give rise to sigma interaction, right? Now, if this is dz2, then this is yz orbital, and these are the conditions. Now you see that if you take, if this is the z axis, and if this is the xz, this is the x, and this is the z. Now we have just rotated it a little. Then these two orbital with the z component will do the pi overlap. That side will be free. And if you take the xy and this dx2 y2, then you can see that this is a overlap, that is here only this overlap comes. I mean, I this is the from this book from molecular orbital, actually they always show that what will be the position. And from another book, this Miss Letter, I kept it for your understanding, to show that where does this overlap go. So here, if you can see, it is the sigma overlap, and tentative thing that shows how the overlap takes place. And these two are pi overlap. And here you can see, this is the overlap with this lateral overlap. This is called very lateral overlap, and it is much more much less effective than the sigma or pi orbital, and this is called delta 1, right? This is called delta 1. And if we go to the, so this is possible. So there are two very important thing that you please note, that when we are talking about the possibility of delta overlap, when we are talking about the possibility of delta overlap, we can see that dx2y2 and dxy orbital both are both can participate in delta bonding, right? So this is the lateral overlap. But in reality, what happens that, as I told you, that here we have shown that these x2 y2 orbital that remain over here, that doesn't participate. Only these four orbitals do participate in delta bonding for the simple cases. I mean, there could be other, I mean, when you will go to the organometallic, and when you will see the clusters, there will be too many metal bonding. So then there, if the energy, I mean, always try to understand that the energy of the system is very important. And if by some geometry, definitely the geometry will decide the symmetry. And then if it is possible, then it can participate there. But as such, for the simple cases, this dx2 orbit x2y2 orbital doesn't participate in this bonding. So theoretically you can see that, okay, I shall show it there. So theoretically, what are the possibilities? This z2 sigma, then sigma star. Can you see this picture clearly?
Yes, ma'am, but you could zoom in a bit.
This much is possible, okay? So I can, in red I can write, so that, so this is the dz2. Now it is clear.
Yes, ma'am.
So this dz2 here, this is sigma, this is the metal, this is one metal, this is another metal, right? So this is sigma. So obviously, as you can understand, if this is the initial position, so it will go down here for sigma, and sigma star is, don't tell me that, ma'am, in the initial state you have shown that the bonding will be less than the anti-bonding. We are not considering in that way right now. I mean, just try to understand this interaction. So this is sigma and this is sigma star, obviously. Now if you take xz and yz, then this is pi. So here we are considering dxy and dyz, and we are considering pi. So this is the pi star. There are also sometimes a change in the orbital this interaction. So this is pi star. And you have, theoretically you have both dxy and dx2y2 you have for delta bonding. And then you can have the um, delta star here, right? So these are the possibility. But what happens, these in theoretically it actually goes like this. and these doesn't form any bond and it remain as and do not participate. It's not non-bonding because there are ligands and they do take part in this, and this is non-bonding. Doesn't participate in the metal-metal bonding. This is the point. So if you have this M2L8, it is like that, and there could be M2L10 also. So there are possibilities definitely. Now this is one of the point. Now what happens? So if you just look at the electron distribution, so what happens electron distribution? So if you just take the rhenium, so in rhenium, if this is the Re2Cl8, okay, this is another thing. This is another thing I have to explain. So, okay, this I shall come. Once you understand this, then I shall come to this. Okay. Now, depending on the system, so now depending on the system, what could happen? So, okay, this is how. So how do we understand that there is a fourth bond, right? How do we understand? So this is generally what happens when you have two metals. So there are other forces like when first thing is that how do we understand there is a metal bonding and why people are thinking of like this. So you just take these two units, right? So these two units, what is happening among these two units? If you just look at this, what is the difference in there? So everything remains, if everything remains the same, then what is the difference? This is the oxidation state of the metal. So the oxidation state of the metal, if changes, you just see that. Do not consider this one because this is okay. I mean, this is there is only sigma and pi bonding, but consider these two where you have contribution. The electrons, the number of electron is such that it can contribute to the bonding delta orbital, right? Bonding. So now if you look at these two, then what is the difference? The difference is in the only in the oxidation state, right? Oxidation state. Now if we look at the bond length, then why do this change in the oxidation number changes the bond length? This was the question. So if you think of that, there is a as this one electron is less in case of, I mean, what is the oxidation state? Let us decide. So SO4 is 2 minus, so 8 2 minus 8 from 8 if you just so 5, so it is 2.5, right? And here so this is 2, right? So if you take if 2.5 is a little more oxidation, I mean oxidized state, a little more oxidized state, and then this MO should have lower ionic radii or metallic radii in that case, but they still then there is a lower in the bond length. And also you have to understand that the overall negative charge on the complex also increases, and that could also lead to the electron repulsion a little bit, but still the bond length decreases, which actually led the people to understand that there must be additional interactions which actually helps in the this metal another fourth bond, and which is different from this state where you have only sigma and pi bonding, and then you have the bonding case in delta bonding. And this is the more, I mean, that as there is a two electron in the bonding electron, so the bond length decreases in comparison to the single electron in the delta bond. Now, did you understand that part? Then I shall go here. But in some cases, you don't see any differences. So, what could be the reason? Is it clear?
Yes, ma'am.
Okay. So, now if you look at the radium system, so you just look at the radium system and you could see that, I mean, if you just look at rhenium, so what are the electron available? Re2Cl4. So this is neutral, Re2Cl4 2 plus. So if here we can see there are 8 electrons available. So 1 2 3 4 5 6 7 8. So this is the case for this one. Now if it is plus, then there is 9 electron. So 1 2 3 4 5 6 7 8 9. And if this is the case, then you have 10 electrons. Now you can ask, ma'am, as you have said that if there are 4 bonds and more bonds, then there will be contraction in the bond. This yes, this uh, bond length. So here it is the case. Now this is also, if you can see that there is only one discrepancy, that is between these two pair. So first let us go to the normal case. So if you just see this one, both the electrons, I mean, this is delta and this is delta star. So if there is no, practically there is no bonding, only the sigma and pi bonding is there. So this is, I mean, if goes to the anti bonding, so bond order is actually a 0 for delta bonding, and then it is reflected in the high bond length for this rhenium. But when you have 9 electron and when you have 8 electron, there you can see it is expected that this one will have, okay, here also, I mean, no, this is not the case. There also, if you just see that this is this content, so this bonding electron in the bonding delta, and so it is the lowest bond length, and here the bond length increases a little. And the explanation is that why these bonding is so the bond length, why this bond length increases a little bit more than expected. So this is not explained exactly. The reasons cited is that as they are approaching for the delta bond, and as they are, I mean, the electron is in the anti-bonding, for that reason bond length decreases. But as they are approaching, so there is a little bit more electron repulsion between these metals, I mean these orbitals, and that actually changes. So this is not very convincing, I mean, like this. But as the reality is that the bond length is a little more high, so there are explanations, and it is that as it is not ionic, I mean not cationic, and it is neutral, so maybe all the effects actually, uh, in addition to the electron in the delta star bond, all other factors actually contributed to the electron, the higher bond length. So, I mean, really, exact explanation is not there yet. Okay. So now, what are the effects of this delta bond? So why? I mean, it is not that suddenly people have I mean tried to understand that there is a delta bond and what is happening. So what is the visual effect? So what do we see? Not in all cases visual, but in some cases the geometry, the color of this. So we go to the electron spectra, but before that, I can tell you and you will understand. So what happens So when there is a lambda bond, I mean, if you just think of these two compounds, and if you just take, there are few examples. So the questions are like these, that these compounds are extremely bright colored, because bright white is bright colored. So if you, I mean, this is just for an explanation. So you have a compound A, you have a compound B, and if you have a compound C, right? And you can see that compound B, you can see colored, right? So compound B is colored. So what you are explaining, that electron is going from one of the orbital to another, and then it is coming back. All these things you can explain. So does it, is there not anything happening in the C compound and A compound? Yes, it can happen. I mean, it might happen that if you go and measure by UV, or if you go and measure by NIR, you will see that they are also, I mean, in case of, if you have you in your eye this, you can see the UV color, then you will see that this is intensely colored, this is not colorless. But as you can only see the visual color, so what happens, that you can see the color which actually give transition within this wavelengths, this energy. And as you can see that if there is a this condition or this condition, then this energy gap is very low compared to any other metal ligand bonding orbital or antibonding orbital energy gap. And that actually helps the compound to be brightly color, I mean the visible color, because this falls in the range of visible spectrum. So this is one of the question that you can face in NET or any cases. People will not tell you to uh, predict that whether there is in delta bond or not, but people will ask you that this is extremely colored, and so you just uh, speculate why it has happened. So this is one of the aspect, and the second aspect is that the geometry, that whether these two are eclipsed or staggered,
Excuse me,
right?
ma'am.
Yes.
Can you explain the delta part again? I haven't got the.
Which part you will tell me, I shall explain it.
Yeah, the delta plus and delta part and its relation with the spectrum and
Now the bonding part or this visible spectrum part?
no means the conclusion that you have drawn. I couldn't understand in
This
relation with
visible
the spectrum.
spectrum.
Yeah.
Okay, okay. I am taking another, because this is the most important part here. Okay, so if you remember that, let's say you have EG, you have T2G, EG, and this orbitals is like this, and you have this uh, pi, sigma, all these things, right? So if you have pi acceptor, if you have pi donor, so we have all these things, that if you have pi donor ligand, then this gap decreases. If you have pi acceptor ligand, this, right? So there is a del zero, and we have last day we have correlated this with the color of the compound, right? So when you have done this AML6 or any AML compound, then you have taken the sigma bonding between metal and ligand, pi bonding between metal and ligand, right? And the consequence of the difference between T2G level and EG level, because that too actually considered the metal electrons. But if T2G from if T2G bonding, electrons can come from ligands and that also can go to this. So this is the energy gap. Let's say it is E1, it is E2, right? So these are the, and here you can remember E2 is greater than E1. Clear? Now, if you in addition, so when you have metal-metal bond, metal-metal delta bond, then in that case, I mean, this XY remains non-bonding, this XY participate in the delta bond. So if you remember that here in T2G, EG, in all these things, when the pi bonding comes, if you total this character, then pi bonding dxy remain as such because it doesn't participate in pi bonding. So these dxy actually from these two dxy from two metal actually participate in the lambda bonding. And now if you see the difference between this lambda delta and delta star. So in addition to all these orbitals, let me try to draw a little bit. It will be very clumsy, but still it is not six orbitals, so I cannot. I just for explanation let me write. So initially there was initially this T2G three orbitals were there, EG was there. The bonding. I am not drawing all these orbitals that is happening here. Okay, initially for ML6. Now once this is sigma bond. Who wants to join now? I just want to see. But if you now think of the pi bonding, do you remember that this pi bonding dxy, dyz and dxz, right? So dyz and dxz, they could participate in pi bonding. So if it comes pi and this pi star, and if dxy only participant is delta bonding, so this is the gap. So if you look at the gap, this gap is very small. If we tell it as E3, then E3 is much smaller than E1 and E2, and this E3 falls in visible spectrum. Visible spectrum means almost 380 nanometer to 680 or 700 nanometer. And we see strong color. Clear?
Hello.
Is it clear now?
Yes, ma'am. Yes, ma'am. Thank.
Okay. Okay. So another concept is that if you take, let me take one example. Like here we have drawn the structure of rhenium, right? So if you have the rhenium, this compound can have this structure or one of the orbital you can just rotate. Just you take one of the rhenium and you can rotate. So theoretically, if there is no rhenium delta bond, then you can see there is a sigma bond. I mean, if you just calculate, you will have the electrons that will have one sigma bond between the rhenium. So theoretically, these two are possible. I mean, if you just think of the sigma and pi bond that I am telling. So if you think of the sigma and pi bond, you will see that these two possibilities are there. But if you take one of the example is osmium to Cl8, okay, and this is rhenium to Cl8. Now if you just by experiment, if you just see, then you will see that, and as you can understand, we have kept these things a long, we have kept a long gap, right? We have kept these two a wide gap, but when you have the practical compound, the gap is not that much, they are very close to each other. And if you have this staggered conformation, this, then it must be a little bit more stable, right? Because then this space will be, chlorine will be there, there will be no steric interaction. So if you consider the steric interaction, then you will prefer staggered over eclipse, right? And you will see that for rhenium, this is definitely eclipsed because you have this number of electron and you have electron in delta bond. And if this is not eclipsed, if this is staggered, then the dxy, these lobes will be like this, that they will rotate and they could not participate in the staggered form, and it will be like this, right? Who wants to join? I mean, why people try to join right now? Let me admit him. No, again, he is not visible. Okay, I shall give a little break for after some time I can tell him to join. I do not know whether maybe he has joined earlier. Okay, so this is the point that it is definitely eclipsed. Otherwise, it there the bond length shows that that this is only in eclipse form. I mean, the analysis shows that this is only in the eclipse form. But if you go to the osmium to Cl8, as the number of electron in osmium is increased, and there is a I mean, if delta bond is there, then there are electron in delta star also. So effectively, there is no bonding and anti-bonding. So no bonding interaction actually. So in that case, this remains as staggered, not in the eclipse. So this is another thing that supports the delta bond. Okay. So maybe this is the thing for delta bonding. So let me ask you whether you have understood or not, and then we shall go to a new topic. So now this delta bond, you can have more impact. Okay, okay, I shall come to another point. Uh, and in the case of the clusters and I mean, this is much more complicated, and I shall not explain all this type of bonding. This is the basic. I mean, whatever you do, you have to deal with that basic part, and then you can add up. I mean, if you want three orbital, let's say, so if you want to add three metal orbitals, so what you have to do? So here you have L, 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 right? So in first instance, what you have done, you have from this side, this side, this side, this side. The next instance you have to take. So in that case, it is not dz2 orbital. So that you again have to think that which orbital will participate in Z, this sigma bonding. And then if there is this type of things, then you have to look at the basic things. If the basic is octahedral, then you have to take this basic octahedral, this T, I mean this butterfly shape ml4 unit, and then you have to add 3 ml4 unit. You have to look at the available orbital in that unit towards this side, and then you have to decide, right? So this is a little bit complicated case, and this maybe there will be dealt with in the uh, organometric class. Now there is another concept. I mean, as I am telling concept because this is not yet fully uh, proved. So I am just telling you the concept, but still people are not very convinced and in the paper. So this is the mm, triplet bond, right? So means metal 5 bonds. Right. So there is a concept. I'm just telling this. I can give you one or two papers just to read. I mean, those who are interested, they can read that what they have. They have given some support for this bond, but I mean there are counter support also for against the bond, because if you think of these sigma pi and then uh, delta, then you have only this dx2y2 orbital is available, and probably they are trying to bring that orbital in the if it is possible, because no more orbitals are actually there. This is the only possibility when you have this dx2y2 is again going in bonding accord, I mean like delta bonding. But what happens, as I told you in the this molybdenum case, or in the re2 this cl and with this neutral case cl8 and then ph4 ph. So it's for like this, the bonding orbitals are something that there are some more interactions. So I shall just give these two papers, and if anyone wants to discuss, I shall discuss. Otherwise, I shall not discuss. You just read it, because this is the term. It has come to this scientific scenario about the quintuple bond. Okay. So if anyone has any question, please let me know. I shall explain it once again. I can tell you, because this is a new concept. And then I shall go to this paper for the explanation of the paper. I shall not definitely explain it completely, but I shall explain the concept. So is there anyone? Let me check the. No, no, nothing is in the chat box. So if any one of you is interested to discuss on, or can ask that you have not understood that part.
Ma'am, the paper thing, right? The Trisfat.
Yeah. Okay.
Yeah, I've given a small explanation from what I understood.
Okay. This is the basic concept. It's fine that if you have two enantiomer in a mixture, then it is the paper features that with this trisfat anion was reacted in order to obtain resolution of the universe. So this is the main point of the paper, right? So if you have enantiomers, see, try to understand one thing. There are two concepts. One concept is that if you have two isomers, how can you resolve? This is one concept. So these resolve you can do with this type of concept also, that you take the similar type of thing, anion. Let's say your compound is cation, and you take similar type of things, and then these two will match, and one of them will precipitate out and another will remain in the solution, right? This is one of the concept that. So there are different concepts for resolving the this enantiomer. Is it clear? The second point is that if you have made a compound and if you have racemic mixture, or you have one of the enantio pure, one of the, like you have a compound A in one of the beaker, you have the racemic mixture, two enantiomers, and in another mixture you have pure one of the enantiomer. Then how do you know that which one is pure? So this is what Isha has written is fine. So what is the concept? So if you look beyond that paper, I mean not exactly this paper, so there are concepts are that you take an anion. So the first thing that paper explains, this particular paper explains, that if you want to do that part, then you must have this one. I mean, very rich of the compound like tris fat. When you prepare tris fat, when you purify tris fat, you, and if you use it for this NMR the resolution, then you must have this compound is in enantiomer reach. Is it clear? So you have to take that part pure. Now, let's say the concept is that there are two-person A and B. So maybe they are I mean, like twin. I mean, you cannot as such point. So the person C comes, and for some reason, which is the intrinsic property, like the here is the, it is the symmetry, mostly symmetry, and the whether lambda or delta, this isomeric thing. So it likes one of these A, so it interacts with A. Within the system, it interacts with A. Now if you have these two things, then their NMR is in almost in one case is the similar. Like let me try to explain a little bit. I mean, it's not, maybe I cannot explain it. Like if you take this for this particular example only, yeah. So if you have these three, so these are the ABCD, right? Now, if you have this delta isomer, or if you have this, sorry, lambda isomer or delta isomer, delta or lambda, these are facing similar situations. So these are these one each NMR, they are same, right? Do you agree with me? Do you agree with me that this is the NMR environment of the hydrogen, and whether it is a lambda isomer or delta isomer, I mean, if it is like these, this is, or if it is like this, I mean, it is one of the isomer, one isomer. I shall not right now don't want to determine isomer 2. So this NMR environment for this hydrogen remain the same. Is it clear? Please tell me. For this hydrogen NMR environment remain the same whether it is delta or lambda.
Yes, ma'am, it's clear.
Huh. So if it is like this, then if someone comes, so a C comes, right? And C is not doing anything. I mean, it can do two things. It can have bonding interaction, it can have non-bonding interaction, right? Clear? So this paper is around non-bonding interaction. So bonding interaction is possible for there are compound that one of them is a little bit exposed, then there will be reaction. So I'm not doing. So C is not doing anything. It very silently likes, let's say, isomer one. What is the liking? Liking is in the, it is in the, let's say it is in the form of isomer 1, delta or lambda, what form of isomer 1 or the same symmetry. Here both of them has the D3 symmetry, right? So because and for and D3 symmetry for both of them, but C is form of isomer, so lambda lambda delta delta. So C just come and sit behind it, is not doing anything, just coming in between. Now, if these hydrogens, if something comes very close to this hydrogen, because it is not that always, I mean, you can see the bond, it is not bonding, but it is coming very close and doing non-bonding interest, very coming very close to it. And then the environment of this hydrogen just change and it dissolves, I mean, it shifts. As you know that if there is electron dense thing is come then the this hydrogen, this peak of the NMR peak just shifts, and just simply these things is happening. And then you can understand that this is pure and this is not pure. Is it clear
Yes, ma'am.
for other people? Please let me know. I mean, if you do not understand,
Yes,
let
ma'am.
us. Okay, so this is very simple thing, and if you, I don't think whether Venkat will include it not. In case of lanthanide, this pure compound is resolved by also bonding interactions. I mean, the loose bond is formed, and then there is a bonding interaction. Then again, once it is purified or not always it is for purification, in some cases just to see, so they throw away, I mean, just see that whether it has been we made it, whatever we have made it, it is pure or not, and then we don't use it anymore, but to check, just to check that whether it is pure or not. Okay, so let me take a little 5 minutes break. Okay, so because I you can communicate with your friends who wants to join for this class, can join. Okay, just for 5 minutes. So some people have left, and I hope they will not rejoin. Okay, so the next thing that we will discuss is about the electronic spectrum. So if you think of this electronics spectral thing, then you can remember that one of the most important part of the transition metal complex that we are interested is the color of the compound, right? So this is very very important that you have uh, fantastic color and you can explain the color of the compound, and you can also predict the color of the compound. So what is our job? What we will try to understand that why does this color, whatever we see, I mean, why the compound is that colored, and if we add something, I mean, if you remember, if you have exactly, if you have exactly dry, I mean totally dry, not hydrated one, totally dry copper sulfate, you will see that the color of the compound is white. I mean a complete dry thing. And once you just put a little drop of water, it turns to bright blue. So this is only the thing is that at that time it was an ionic compound. In crystals it was like that. And once you are adding a bit of water, it is surrounded by water, and then this is a coordination complex is there. And this coordination complex, by virtue of forming, I mean, just for the effect of this formation of this complex, there is a change in the electronic structure of the metal, and then it gives the color, because now the electron transition is in the visible region and you can see the color, right? So now let us see that I mean, how do you have any idea about the electronic spectra, microstates and all these things? Please let me know, then I can use some terms, otherwise I have to tell very from very basic things. So have you any idea? I don't know. Are people there in the room? So, do you have any idea? I am asking the BSMS students. Do you have any idea about the microstates or the spectral thing?
Um, no, ma'am, we haven't come across a microstate thing.
Microstate you have not done, right?
Yes, ma'am.
Okay. So let us first start with this thing in a very very casual manner. Look, so what we are doing, we are interested. This is the electronic spectra of transition metal complexes. As you have,
Ma'am, you are not presenting.
okay, sorry. Okay, so I have just written this is complex. So we are going into a electronic spectra of transition metal complex. So if I say a spectra, so how does it represented it? So I just kept one. This is the presentation of spectra. Like if you are working in a lab, it's unfortunate that you could not start, but if you are in a lab and your teacher says that you have synthesized some compound, and then you have some colored compound and your teacher says that you just go and do a spectra of this. So what you will do, the process is that you take a very little amount of sample that is defined. I mean, it is 10 to the 1 minus 3, 10 to the 1 minus 4 molar solution. So let's say 10 to the 1 minus 3 molar, 10 to the 1 minus 4 molar solution. You have to prepare and you have to check before that in which solvent the compound is soluble, right? Then what is the solvent you have to take, either polar, non-polar, and you have to make sure that when you are doing the spectra in the UV visible in the machine. So there are different type of spectral machine. I mean, there is general term, the UV visible spectra is called electronic spectral over here, and there are machines for these UV visible. Then you have emission. All instruments are different. There are other instruments that also use UV visible. So you go to the machine, you have to measure, you have the cuvette thing, you take a sample solution in the cuvette, but make sure, you have to make sure that your solvent doesn't give any color in this range, so that you have to make a baseline correction, all these things. And once you do the spectra, and then what will happen, it will show a spectra like this. It might show like these, right? These type of spectra you can see. And then when you bring it back to your teacher, so your teacher sees the spectra, and then he will, the next step, he will try to understand that what is the transition for this lambda maximum. This is called lambda, and these are the lambda max value. And then you will try to assign some lambda max values you want to explain. That if you have taken a particular ligand, and also there are something that's comparison. Let's say you have nickel H2O whole 6 2 plus, and you have prepared a ligand with nickel L whole 6 2 plus. So let's say the first one is like this, and then your compound is showing like this, right? So then he will, or he or she will ask you to explain the deviation from these other value and what is happening, and why also it may be explained that why intensity of the one of the peak is uh, different from the other. So all these things comprises of the electronic spectral presentation. Now the point is that how do I know? So what till now for the bonding, what have you understood, that there are this T2G level, EG level, this the E orbital thing that you have learned. But when we come to the spectra, then you know that this energy is involved, and then actually an actual energy is involved. Then for understanding that in the initial phase, we do not take directly the um, this T2G EG, this diagram, this um, bonding in anti-bonding interaction, these diagram we do not take directly. We need to take some, we will approach it from the quantum mechanical perspective, and ultimately we will come to this part. I mean, this is the beauty of these things, because first we have to understand this in some way, and then we have to go to this is allowed and this is not allowed. There are certain things, all the things will be explained. Today I am a little bit slow, so that because this is a new thing, and that you try to understand slowly. So next, what is the point, that if we just think of the part that you have taken it to the instrument, and what is happening. So the thing is happening is very simple. You have very narrow slit, and through this slit in light is passed through this, and you have the quartz cuvette. Right, you have the quartz cuvette, and the light is going, and it is going beyond this, and it is going through the solution. And what is happening during the solution? Some of the light, a portion of the light is absorbed, and the rest is uh, going out of the system. So if you have this I is the original light, and if it's what is and what it has absorbed you cannot measure, so what you can measure, that I0, that what is coming out. So if you do this, then it is the absorption that we see. Now what absorption then we see? So if this is the color range that it absorbs, this is the energy that absorbs, then what color do you see? You see the complementary color for the compound from outside. So in that way we can uh, this present the spectra, and we can predict. But now, okay, let me give one more page here. Okay, so when actually we are mathematically try to understand, then we do not take it in that way. I mean, it is not the T to G level. So what really we do? So we approach in quantum numbers, through quantum numbers approach. Okay. So here I shall not explain the quantum numbers or whatever the things, all you know. I will just take the values for this, how do you do it. And here, very simple thing, let me just tell for this very basic purpose, that we have to understand that the electron is spinning around in the orbitals, and for that there are some magnetic moments are generated. So there are interaction, the spin quantum number, the magnetic moments, and the Once you see that I am not in the call, please call me. So can you tell me that how much? I mean, where I stopped. I mean, where from where you couldn't listen. Please let me know from where.
Ma'am, you were telling about the spin quantum number and tranquil quantum
So
number.
it is fine, right? Whatever I wrote is right.
No, ma'am. Microstates we have not.
No, this one. Up to till this one. Till this one is right, okay? Till this one, you know.
Yes, ma'am.
So now we are going to the microstate. So can it is presenting, right?
Yes, ma'am.
Okay. Now you can keep this P2. So this is very simple case, and this plus 1, 0 and minus 1, right? This is plus 1, 0, minus 1. Now, how many ways we can distribute? The first thing is that you have to know that how many ways you can write. You can write anything, okay? And then you have to choose that what Pauli's exclusion principle you have to give the Pauli's exclusion principle. Then you have to look at the Holmes rule. So these are the, I mean, and many more I am writing, and then I shall go to this. A little more let me draw, and then I shall go to the. So I can draw. Anything I can give, I mean, whatever possible. And then we can write in this way. So there are many possibilities. So I shall tell you to take just one case, one P2 case, and then you can try to draw it. And now how do you give the number? So here, if you just see that it is not always possible to write plus up. So this plus up you can take as plus value, and minus up you can take like minus value. Now, if you just take it, so this state corresponds to 1 plus and 0 plus. This is 1 plus and minus 1 plus. So, is it clear? This part you have to be clear. So, how do you present? So, this is 1 plus 0 minus. This is 1 plus minus 1 minus. Let me know, clear or not. Look at it very well and then. Is it okay?
Yes, ma'am.
Okay. Now, if you take it, then okay. So this ML is equal to ML is equal to summation ML. M is equal to summation. Yes, that is known. Now, if you take, so this is the best way to write this. These are the, but here you can tell, I mean, I'm writing. writing that why this value is not there, right? So if it is plus 2, then what would be the thing? That 1 plus 1 plus. I mean, if this is this value, then it must may have this value. So what is this value? So how do you exclude? So is it possible to write? Does it allowed? Is it allowed to write?
No.
So here what I told you, so you can write anything. You can write this one. Here you can write this one, but there are possibilities, enormous possibilities, that if you want, you can write all the possibilities, and then you have to cross this one, because then first you have to, how many ways you can write, then you have to consider these two, and then if you come, you will see that these two values are these values are only permissible values, right? These are the permissible values that is possible, and here it is the total m. I mean, ml and ms, why it is written? Because this is m. When it is plus 1, this is the value. This is the case. It is possible, because this is the most possible case what we write, and here it is ml is equal to plus 1 and 0. Sorry, this one, not this one, not this one, this one. This one. This one. Value. See, plus up and minus up. So ms equal to 0. Summation ms is 0, and it is in the one this case. So plus 1, 0, minus 1. Okay. So this is the, so ml value in that case is 2, and then ms value is this one. Please look at the picture. If there is any difficulty, please let me know. Just look at the picture, nothing else. So let me know from all of you, almost all of you, that whether you have understood or not. Please let me know. You can write in chat, or if you find it something is problematic, let me know, because this is the basic part. If you understand that, then everything is quite clear. Okay. Clear. Okay. No, sometimes people, I mean, because here it is D, and after some time it will be very difficult to understand, because too many things are there. Okay. So these are the allowed. So now what are the labels over there? These are the allowed things. These are allowed. Now, out of these allowed, we will go to pick up the ground level, right? Now you have 3 ions is described by 2s plus 1 Lj. So J value, for this time we will not take the J value, we will explain, we will bring the J value some after some time. But Russell not complete, let us understand the this 2s plus 1 L value, then we will come to this. Okay. So this 2s plus 1, so 2s plus 1 is the spin multiplicity, and if L is equal to 0, so if L is equal to 0, then this L is equal to 0, then we say that's S. If L is equal to 1, we say P. If L is equal to 2, we say D. And if L is equal to 3, we say this is the F symbol, right? Now, and S equal to again you have to summation ms, means if all of them are paired, sorry, all of them are paired, you have s is equal to 0. If you have all of them, one of them is unpaired, then you have half. If you have two of them, like if this is the case, then we say this is 1. So in that way it goes, right? And then we have to see at the lowest value. So for 2p, what is the so we can say that for 2p this term is actually the value that is with just a minute. This is the term, so this is the highest ms value, like it is this value. Just a minute, let me just see. I just forgot, just a minute. Okay, so now if we come to the ground state, so what about the ground state term? So what actually that explains? The ground state term is like this, that if you have a transition, you have, this is the ground state, and you have the other state which are called maybe excited state. Why? Because if you put energy, then if electron is in the ground state, it might go here, it might go here, and it might go here. And these states are derived from these microstates, and these are the, I mean, now we will find out the ground state. So the first is that choose maximum L value. Okay. So the maximum L value here is the maximum L value is +1. So you can take these one. Sorry. You can put this one. 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 So there is a maximum L value of +1 in these 4 cases. And then you choose maximum S value. Right. So this is 2. So this is maximum S value is 1. So here, as I told you, this is the ground state. So these 2 is the ground state, and this is the ground state. So now if the value of L is 1, then this is the S symbol, right? And if L is equal to 1, this is the P symbol. So our symbol will come as P, right? And 2S plus 1, so the symbol will come as P. and 2s plus 1. So half and half, right? So these 2 is equal to half plus half is equal to 1. So s is equal to 1, and if s is equal to 1, then 2s plus 1 is equal to 3. So right now this is 3p is the ground term, right? Now this j value, uh, okay, as it is there, we can say the smallest j value if orbital subcell is less than half filled, and largest j value if orbital subcell is greater than half filled. So L is equal to maximum 1, and this is in that case more than half filled, sorry, less than half filled, is the smallest j value. So smallest j value is always 0, because uh, this is, I mean, this is the half filled case, and this is the less than half filled. So L plus S, and J is the spin orbital, L plus S, and this is here it is 0, because L plus to L minus, and this is the point that when it is less than half filled, then you have to take this lowest value, and when it is more than half filled, you have to take this value, and for that reason at this point you can take the 3p value. Okay, now what are the other values? So this is the ground term, but I shall encourage you to find out one or more values. So if this is the case, then it is 0. So this is the S, right? And again this is S, and 2S plus 1 is 2S plus 1 is 3. So this is the 3S term. And what is this ML? So 1, it is 1. So again P, but here also this is the same. I mean, this is degenerate thing. I mean, in that way these two are similar. And then this one is again 2s, so minus of so minus 1, right? And if it is minus 1, then 2s plus 1 is equal to 1. So this is, okay, you please do it. I mean, I can, this is 1s. This is 1s. Right. So in that way, you have to do the ground term. First, you have to find out the ground term, then the other terms, and then you have to arrange you don't have to arrange it right now. You have to, I shall not tell any more. You have to arrange it according to the, I mean, this uh, I mean, there is a Tanabe Sugano diagram. I shall come not next day, but after that diagram that will tell you that what is the energy of the system of the microstates, right, corresponding to this. And also what we will do, we will with d orbital. So here we have done it for only p orbital. So if you take d orbital, these are the terms. And what how would you do it? You don't have to go to all these clumsy things. What will you do? You will just take, and whatever you have learned in the first place from Hund's uh, maximum multiplicity and this Pauli's exclusion principle, you just put electrons in that way and you find out the ground state. But this is the way that I have shown you. And then once you know the ground state from the uh, like here you have done it like that, and you can put it in the next, you can put it here, you can put it here. So for highest, they will remain, the S value will remain the same, only the L value will change, and then you can put in different way, and you will find that it will come according to the energy. Okay, I think I must not discuss any more because it will be too much. And then we will go next day, we will just arrange it and we will go directly to the spectra. And in the spectra again, what will happen? When we will discuss the spectra, we will not even ask any, we will not take this microstate as such. We first will see that what is the color, and we will include the Jantelar distortion. We will again come back to the this orbital diagram to understand the pure spectra. And then, of course, we will go to the Tanabe-Sugano to understand the fine structure of the spectra. Okay, so if you have anything from these, please ask. So do you have anything? I mean, this part is very easy. I don't think you have anything to ask.